Good day all. I am Sedra, a fourth-year pharmacy student from Ain University.
And my name is Ismail Moumen. I'm a fifth year pharmacy student at Ain University.
And today we are going to present a molecular modeling study on the human equilibrative nucleoside transporter 1, permeants and inhibitors, and implications for anti-cancer and cardiovascular drugs. The human equilibrative nucleoside transporters, which are abbreviated as hENTs, are a family of integral protein and mostly found on the cell plasma membrane. hENT's main function is to transport vital nucleosides and nucleobases, which are essential for the DNA and RNA synthesis. Pharmacologically or clinically, the isoform hENT1 plays an important role because it is a major double drug target. Mainly, the hENT1 is a target for drugs that are either permeants or inhibitors. First, let me explain what permeants are. So basically, permeants are molecules that permeate through the transporter by inducing conformational changes within the transporter, leading to the movement of molecules from outside to inside the cell. Often, these permeants are anti-cancer agents. Once permeated, these anti-cancer drugs, they get incorporated into the tumor-replicating DNA, inhibiting the DNA synthesis and stop the growth. On the other hand, inhibitors are molecules that bind to the transporter, gets stuck within the transporter, leading to the inhibition of nucleosides passage. These inhibitors are important as cardiovascular agents, such as antihypertensive and antiarrhythmic drugs. Binding of these drugs to the hENT1 as inhibitors inhibit the transport of nucleosides such as adenosine into the cell and leads to its accumulation extracellularly. Now, the accumulated adenosine outside the cell will bind to plasma membrane adenosine receptors, resulting in the activation of intracellular signaling pathways that protect the heart.
This brings us to the question of the study, which is what we will achieve from this study. Simply, the answer is the distinguishing between both the permeants and the inhibitors, as they both bind to the same binding pocket. Furthermore, to develop the pharmacophore for each class of the drug, as the permeants pharmacophore will aid in the development of the new anti-cancer agents, while on the other hand, the inhibitor pharmacophore will lead to the development of some new cardiovascular agents. And it's also important to note that the current inhibitors, they have poor pharmacological profile. Our aim in this study is to develop a computational approach for the drug distinction and the discovery of the permeants and the inhibitors. This will be achieved through these following steps. One, collection of the known hENT1 permeants and the inhibitor from the literature. Two, develop pharmacophores for each. And the final step is the validation of the pharmacophores.
Now, how we carried out our approach. First, 17 permeants and 60 inhibitors were obtained from the literature using several search engines, such as Scopus and PubMed, and were drawn in the molecular operating environment software as 3D structures. After that, the compounds were washed in order to make sure that the maximum number of possible conformers of each molecule has been covered by creating the tautomer state using the MOE wash function. This to ensure that all the biologically active forms of the permeants and inhibitors have been covered in our database. All of these three steps were for the sake of preparing the database that we will use it for the selecting of the training set. Now, the selection of the training set wasn't randomly, but based on a specific selection criteria. First, the criteria was dependent on the rotatable bonds, in which the lower, the better, because they are more rigid, and thus we can identify their active conformation rapidly. Second criteria was the molecular weight, where the small size is better. Lastly, potency, whereby high potent compounds are preferred. Moreover, belonging to different scaffolds is important for selection. And therefore, 2 permeants and 4 inhibitors, one from each scaffold, has been chosen or have been chosen as training sets.
The fifth step of the methodology was the pharmacophore generation and the elucidation process, which has the following steps. 1. Training set was prepared based on the rotatable bonds, molecular weight, Km, and Ki values. Second step was the superimposing of these ligands using the MOE software. Third step was the elucidation of each class separately. And the final step was the generation of the pharmacophores, and these diagrams represents the elucidation and the pharmacophore generation for both the permeants, and the upcoming slide represented for the inhibitors.
Now, our last step in the methodology was the pharmacophore validation, where the pharmacophore queries were validated using a test set of known hENT1 ligands, which were either permeants or inhibitors. The top 50 elucidated pharmacophores of permeants and inhibitors were validated by passing a washed testing set of known hENT1 ligands through each pharmacophore to give true positives and true negatives. According to our count of true positives and true negatives, we could calculate the selectivity and the specificity as using the shown equations. Basically, selectivity assesses the efficiency of the developed pharmacophores in selecting the desired ligands, which are indicated as true positives, while specificity measures the pharmacophore efficiency in eliminating those ligands that belong to the other class of hENT1 ligand, which were added as true negatives in this case.
Our results were clearly significant. As for the permeants, we have generated a tens of pharmacophores, and then we have calculated their selectivity and specificity. Then we found the most performing pharmacophores, and we have successfully chosen pharmacophore number 23, which has the following feature. It has one aromatic planar system, two hydrogen bond donor projection, one hydrogen bond acceptor, and it have successfully scored a selectivity rate of 100% and a specificity rate of 84.62%. And on the right-hand side, we can see the 3D pharmacophore for the permeants as well as the generalized pharmacophore for the permeants. The same thing was done on the pharmacophores, and we have for the inhibitor pharmacophore, and we have choose the pharmacophore number 36, which has the following features. Hydrophobic center feature was 1.2 in the diameter. Hydrophobic feature was 1.4 in the diameter. Hydrogen bond acceptor projection, aromatic or hydrophobic center feature, and it have successfully scored a selectivity rate of 92.3% and the specificity rate of 87.5. And also we can see its 3D structure for the pharmacophore as well as the generalized pharmacophores. Furthermore, the permeants and the inhibitor pharmacophores were further validated using the virtual screening technique that it allows not only us to test it theoretically but also practically, as this process was preceded by the following: 5,000 ligands, including 56 known inhibitors, were choosing, then passing them through either one of these three: the standard protocol, which docks them directly inside the hENT1, and the second one was the filter protocol number one, which filters the ligand in by passing them through the inhibitors pharmacophore, and the filter protocol number two, which filters the ligand by passing them through the permeance pharmacophore to filter them in by passing through the and filter them in by passing through the inhibitor pharmacophores. And the next plot, it illustrates both filtered based protocol and the standard protocol, where we found that the filter-based protocol was more superior than the standard protocol in the terms of the efficiency. For the example, in the top 20 ligand percent that was docked inside the hENT1, using the standard and the unfiltered protocol resulted in the retrieving or the obtaining of 60% only of the inhibitor. On the other hand, the filter-based protocol achieved 100% for the inhibitors that were retrieved. As we also found that the filter-based approach was 5 times more faster than the standard protocol, as well as it was superior in its efficiency.
In conclusion, we report the successful development of highly sensitive and selective pharmacophoric models for permeants and inhibitors. These pharmacophores could play an important role for developing novel anti-cancer and cardiovascular agents. Also, the study demonstrated a new virtuous screening protocol whereby the aforementioned inhibitor pharmacophore was used as filtration tools. This work has been accepted for publication with minor revisions in the Jordanian Journal of Pharmaceutical Sciences. Thanks for listening to our presentation.